Subscribe to my channel and press the bell icon for latest notification about my videos. Welcome to all of you. It is a new module of work, energy and power. So basically what we are getting that in this module we will be dealing with work, power and energy. This work, power and energy are very much similar and co-related terms. So in this module we will be dealing with work, concept of forces, conservative and non-conservative forces, that is variable and constant forces too with them, and work energy relation, that is a work energy theorem, energy, that is kinetic and potential energy, and at last we will be dealing with power. So let's start. Now we are beginning with the topic of work. At first, what strikes in our mind, that is anything which we do in our normal life, it is doing some work, doing anything, but in the language of physics it is something different. Physics states that work done is equals to the scalar product of force into displacement, that is S, or in bracket you can write it as displacement. So what is the reason behind this force into displacement? Was because work done is normally proven to be the scalar or dot product of force and displacement. So what is this force and what is this displacement? We'll be dealing with just with an example. Let us say a block is there kept on a horizontal surface of mass m, and a force is applied, suppose in the random direction, okay, and due to this force there is a displacement of the block in any random position whose distance from the starting point supposed to be s, that is displacement, and the angle between these 2 points is supposed to be theta. So what we are getting is that this work done over here be equals to F vector dot S vector, and we know that the dot product of two scalars give us an angle of cos theta. Now for the field of physics, if we try to understand that the component of this particular force in the direction of the displacement will be equals to F cos theta, and this F cos theta will multiplied with this term S, we directly get the result of W equals to F cos theta. So this is basically the basic introduction of work done in terms of physics. Let's proceed further. There are certain conditions for various types of work done which depend on this angle theta. First case, it is case 1, when theta is equals to 0 degrees. Suppose that the force vector and the displacement vector are both in the same direction. So at that time what we are getting, that W will be equals to F dot S, simple as because we know cos 0 degree, as if theta equals to 0 degree then cos of 0 degree equals to 1, so this will be equals to simple F dot S. Second case is when theta is equals to 90 degrees. At that moment the force, suppose the displacement is in this direction, the force will be in this direction, or it may be in this direction. At that moment the angle between them is 90 degree. So what we are getting is that F dot S equals to 0, as cos 90 is equals to 0. Third case is seen when our theta is equals to 180 degrees. At this instance, if the force and the displacement are totally in opposite direction, then we are getting that W is equals to minus of F dot S. Now these two statements are quite interesting and peculiar, so let's discuss them in an elaborate manner. When theta is equals to 180 degrees, the work done is negative, and when theta is equals to 90 degrees, work done is 0. So let us define them in a elaborate manner. First, dealing with this 90 degree case. For an example of the gravitational force, our earth is normally a partially spherical, not totally symmetrical sphere, and we are there on the surface. We all know this, and the force of gravity attracts it towards its center. Suppose it to be center. Now the earth is rotating in this direction on the basis of its axis. So the force over here must be something like this. The displacement is something in this direction and the force is towards the center. But normally, to say our displacement, or in an elaborate manner, if this is the block which we are dealing with for the first case, the macroscopic view, if you see that this is the surface of earth and this to be the block, and if we move this block in this direction due to a certain force, and it is displaced to a point with displacement s, but the force of mg was acting downwards. So this force is a workless force on this mass, as because the displacement of this mass is due to this external force, and its gravitational force makes an angle of 90 degrees. That is, F gravitational is perpendicular to the displacement. So this Wg, or gravitational, is equals to 0. I hope it's clear now. Now secondly, we are having the 180 degree case. This is elaborately explained with the help of our frictional forces. That suppose this to be the same mass block and this to be the surface, we are applying a force in this direction and it is displaced till here, but there is a coefficient of friction on the surface, mu, to be suppose maybe anything, maybe 0.1 or something like this. So due to this frictional surface, rough surface, or external frictional force is also acting on it. So what we are getting, that the displacement of this block is normally due to this F external. If this condition, there is a condition, if F is lesser than F external, then only it is satisfied, otherwise it will be not moving only. So what we are getting, that this F external will deal that F external dot displacement will be given by work external, but for the work due to this frictional force will be simply F W frictional is equals to frictional force into displacement. And what we are seeing, that the displacement is in this direction and the frictional force is in this direction, so the angle between them is simply 180 degrees. So what we are getting is equals to minus F dot S. So I hope these two statements are clear. Work done is a physical quantity, so it must be having certain units. Now we know that work is equals to F dot S from our entire study till now. So what we know, that this unit of force is Newton and displacement is meter. So normally we should say that work done, units work done will be equals to in Newton meter. Plus Newton meter in SI preference, that is our international system preference, standard preference, we know that this is equals to joule. So why not now? So what we are getting, that work, the standard unit of work done is represented in joule. Now there are certain other units, commercial units too, of work done. For example, urge, electron volt, calorie, kilowatt hour. For reference, we should say that this urge is equals to 10 to the power minus 7 joule. 1 electron volt means 1 urge, and 1 electron volt is equals to the charge of 1 electron run through 1 volt potential difference, which is equals to 1.6 into the power minus 19 joule. And calorie, for suppose obviously 1 calorie should be equals to 4.186 joule, and 1 kilowatt hour is equals to 3.6 into 10 to the power 6 joule. We will be dealing with this topic in our next classes, and this calorie unit will be discussed in our topic of heat and thermodynamics. This electron volt will be dealt in the chapters of electrostatics and electrodynamics. This urge will also be dealt with some topics. Now basically we don't have to learn this entire factor, it will be generally given in our question paper, but something we should know, that is this 1 electron volt and this 1 kilowatt hour, and basically the value of 1 calorie is quite remarkable, and it gets day-to-day flow. So let's proceed further. What is energy? What are the types of energy? And what is the basic unit and use of energy? Energy is the basic requirement to do work. Without energy, no work is possible. So it is quite common to be curious about the similarity between energy and work. The two physical quantities are a bit similar, as because they are interrelated and share a common unit and dimensions too. But normally we say that energy is the unit of doing work due to the virtue of motion or at rest of the object. Suppose a block is displaced due to a force till a certain measurement to be S, so we normally say that W is equals to F dot S, or F is cos theta. But the energy required to give the object, this particular object, a force due to which it gets into a motion and comes to rest at a certain point, this particular form of this motion is termed as energy. Energy is a quite deep and essential term which is dealt in our quantum mechanics too, but at this moment we are going to get a very basic idea, an elementary idea of the term of energy. Now energy is basically of two types, that is, it is of two types. First one is our kinetic energy, or the energy associated with the motion of a body, and secondly we have potential energy, which is associated with the rest position of a body. Now we basically see that this kinetic energy is represented by a term of half mv square, whose derivation is quite basic and elementary, and potential energy is basically rest and height, so it is represented by mass into gravity into height, mgh. Sometimes it is represented by E suffix k, and sometimes it is represented by E suffix p. A boy is there who is throwing a ball in the upward direction. The ball will reach a certain height, and then it will obviously come down, hit the ground. So at the initial point the ball is having its maximum velocity. Here v is maximum. It will be gradually going upward and decreasing, keep on decreasing, and at this final height or maximum height, h max, suppose the height over from here to here is h, so at this maximum height point the velocity will be totally zero. So the ball or the object will be at rest for some fraction of second or very few times, then it will acquire gradual energy and it will be dropping, coming down, and at this instant its velocity will be maximum. So if you plot the displacement versus energy curve, suppose this to be the plus x direction, this to the minus x direction, and this to be the energy or maximum energy over here, energy graph. So what we are getting is that kinetic energy at this instance, suppose at this first initial point, it is gradually in a decreasing manner,
it is maximum at the first point over here, and it is gradually keeping on decreasing and coming over here. At this instant, this kinetic energy is approximately 0 for some instance, and again when it is coming down from here, it is gradually increasing again and reaching a maximum value over this surface, its ground. So this is the kinetic energy variation with displacement and energy. We must be having doubt of this minus x and plus x. This minus x and plus x are basically our Cartesian axis, and this x refers to displacement over here. So at this moment, as we are getting that, it is our reference point, so it is increasing from here to 0, and again it's coming down to maximum, so it is minus to plus. And further we say that the potential energy over here, for what we are getting, that at this ground level the potential energy, as it is mgh, and due to this h is 0, so potential energy over here is 0. So potential energy's curve will be gradually increasing, and due to height as increasing, so it will be gradually increasing and reaching a maximum value here. So at this instant, the potential energy PE will be maximum. But after it, as it is gradually coming down and the height is decreasing, so it will be similarly, it will be coming down and reaching over here. The graph. So this common graph of kinetic and potential energy is represented like this, and the common energy, to say the total energy associated with it, is given by this E is equals to kinetic energy plus potential energy. So it was the elementary idea of energy. Now we are going to deal with the most awaited topic of this chapter,
That is our work energy theorem. So work energy theorem,
by this name, the basic glimpse what we get about this entire theory is
the relation between work and energy.
So as we have dealt earlier that work and energy are very much similar and co-related terms,
The relation between them
is given by this work energy theorem.
Now, from the elementary ideas of kinematics, we have certain formulas in which there is a relation between velocity and acceleration and displacement, that is v square is equals to u square plus minus 2as. So by simple manipulation, we can say that v square minus u square is equals to 2as, considering the positive acceleration value.
So if we multiply this entire equation, suppose this to be equation 1,
by m by 2, what we are getting? We get m by 2 into v square minus m by 2 into u square equals to m by 2 will be cancelled, that is m into a into s.
as multiplying both sides by m by 2.
So what we are getting is half mv square, which is equals to kinetic energy, and this half mu square is equals to initial kinetic energy, and this m dot a is equals to force, and this s is equals to displacement.
So what we are getting is that change in kinetic energy is equals to work done, which is nothing other than work energy theorem. This is everything about work energy theorem's derivation. If it is a question of 2 marks, then we can say that this is the very simple derivation of the work energy theorem. Now in practical world, this work energy theorem is very important. In order to deal with this work energy theorem, we are having certain concepts of forces. There is conservative and non-conservative forces, which we will dealing further. This conservative and non-conservative forces makes the entire calculation of this work energy theorem. This work energy theorem is totally blank without conservative and non-conservative forces. So let's see what is conservative and non-conservative forces. So what are conservative and non-conservative forces?
Conservative forces are those forces
where the work done on a closed loop is 0. To be saying in elaborate manner, the forces that are path independent means doesn't depends on the path. For example, the gravitational force of any object on the surface of earth, if this is the surface of earth, if an object is thrown in vertical direction, it will be coming down in this direction, or it may come down in this direction, but everywhere the force due to gravity will be same over mg if the object is of mass m. So this will not depend on the direction that it follows this first path or second path. Both the cases the force of gravity will be mg, so it is a conservative force. For example, our gravitational force, electrostatic forces, magnetostatic forces, etc. So non-conservative forces are those forces which follows the path, means depends on the path. For example, the forces of friction will obviously depend on the path. As to say, if an object is moving in this direction and the same object is moving another rough surface, then the coefficient of friction will be different for both the cases. So frictional force will be path dependent. That is why it is a non-conservative force. So it is the elementary idea of conservative and non-conservative forces. Now the manipulation of work energy theorem due to this conservative and non-conservative forces is very important. So let's see that. Delta K is equals to work done, which is our elementary idea of work energy theorem. But for conservative forces, this work done is also equals to negative of the change in potential energy. So it is quite important to note that for conservative forces, this is also a rule. There is also an important manipulation of conservative forces, that is work done is equals to summation of kinetic energy plus potential energy at any instance of the path, as it is path independent. So suppose there is a circular pathway traveled by any object, this object m. So the summation of kinetic and potential energy, or to the total energy to E total, will be conserved or constant at any instant. Suppose this point to be one point, this is the second point, this is the third point, or any point. At every point in the entire path, the summation of kinetic and potential energy, the total energy will be conserved. This is the basic and most important fundamental rule of conservative forces for work energy theorem. In relation between kinetic energy and momentum, that is P. So we all know that half mv square is equals to kinetic energy. If this factor is multiplied and divided by m, so what we get? Half mv square into m by m will be equals to 1 by 2m into mv whole square. And we know that P is equals to mv. So imply here P square by 2m is equals to kinetic energy. Now we are going to deal about spring forces. So suppose there is a surface, something like this, and a spring is tied from this surface to a block kept on the surface of mass suffix m, and this to be the equilibrium position where the entire system is stable, so where x is equals to 0. Here the force applied by the spring is also 0, and the displacement also 0. But suppose we apply a force in this direction, that is, we are compressing the spring. So what will be the resultant action? If we compress the spring, then obviously the mass will be repelled by the spring in the opposite direction, which is the spring force. So if we consider the spring force to be 0 over in this case, then in the second case, when we apply external force and the spring is compressed, the spring force will
be in this direction after this action, where the displacement of till here to here is supposed to be x, and here it was x equals to 0. So here Fs is positive in nature, as it is applied in the positive x direction. If it is simply in reference with the Cartesian axis of coordinate system. And in the third case, suppose if we stretch the spring, if we are stretching the spring in this direction, so it will be coming something like this. If this was the initial point, this has made a displacement over here, suppose x displacement. The spring is having the tendency to come back to its equilibrium position, which is at x equals to 0, by applying a spring force in this direction. So here Fs will be negative, as it is going away from the mean position in the negative axis, so it is a negative force. So if we plot the variation of spring force and the displacement something like this, that is the force Fs and x, what we are getting is that the force and displacement is not always positive. Sometimes it is negative too, passing through the origin. And if we say that the force at any instant, suppose the force is positive, then the displacement is negative, suppose at this instant. And if the force is negative, then the displacement is positive. As this force is negative, spring force is negative, the displacement is positive, x is positive, and here x is negative. So the variation is something also over here like this. So what we are getting, that the area under this curve from suppose to x sub x m is the distance over here, then the area on the shaded region will give us the work done for moving the object from x equals to 0 to x suppose to x sub x m, which is also given by the equation of f equals to minus kx. Putting this in our simple equation of work done, which is equals to integral of f dot dx, that is fx dot dx, what we get is from 0 to x sub x m minus of 0 to x sub x m, as we know that fs is equals to minus of kx, the minus of kx dx, and as k is a constant, this is the Hooke's rule, that force is equals to minus of displacement is k is the Hooke's constant, which value is dependent on the material of the spring. So this k is a constant will be coming out, what we will be getting that minus k is coming out, and we know that the integration of x dot dx is x square by 2, and the limit is from 0 to x sub x m, so it will be simply equals to minus k x sub x m square by 2 minus 0. So it is the work done by the spring force. Work done by variable forces. The forces which we are dealing till now were constant forces. Okay, means having any magnitude, a particular magnitude value, the Newton, 3 Newton, something like that. But for variable forces, suppose the force to be F Newton. The value of F can be anything, any natural number, any integer. Delta K is equals to W. We also know that kinetic energy is equals to half mv square. So if we differentiate both sides with respect to t, what we get? We get dk dt or ddt of k is equals to ddt of half mv square, or dk dt is equals to ddt of half mv square will be equals to m will be coming out as a constant, and dv dt into v, as we know that ddt of v square is equals to 2v into dv dt, as it is differentiated with respect to t and the constant over here and the variable here is v. So it will be m dv dt dot d, or dk dt is equals to mv dot dv dt. Now we know that dv dt is equals to acceleration m into a into v, which is equals to f dot v. Can we write that f is dot dx dt, as dx dt equals to v, dk dt equals to f dot dx dt. You can cancel dt from both sides, and what we are getting over here, dk is equals to f dot dx. Integrating both sides from
K initial to K final and initial position to final position. What we get? We get Kf minus Ki is equals to work done. Is the work energy theorem for variable forces. Work done is equals to negative integral of F dot dx. Most important and fundamental concept which can be applied anywhere in any numerical for variable forces or work energy theorem. There is another method of finding total work done by a variable force. It is a graphical method. Force versus displacement graph. The variation of the force and displacement for an object is something like this. So we can take out the total work done by the object in this path by this force by simply calculating the area under this curve by simply taking a fixed strip of dx length, small strip of dx length, and multiplying this f dot dx, which is simply nothing other than this, and integrating the entire factor. If it is very much symmetrical object, however the square is there, the graph is something like a square, then we can simply take out the area. But for this kind of variable force and differentiation, we can simply apply our w equals to minus f dot dx. This minus sign is basically due to the conservative forces, that is sign. This negative sign implies that the object which is exerting the force is making the displacement away from it, which indicates the negative sign. So it is all about work done and energy with variable forces. So what is power? Power is nothing other than the rate of doing work. The rate by which we do work is termed as power. It's simply P is equals to dw dt or ddt of w, where w is the work done. If dw equals to f dot dr or w is equals to f dot r, by putting this value in this equation, we get that P will be equals to ddt of f dot r, ddt of r, as f is coming out, as because here f is constant. And why this f is constant? At any instant of time during any path, at any particular instant, suppose this to be the work done by an object, so at any particular instant of time the force applied will obviously be constant, having any particular value, it will not be variable. Also, so x is constant oriented, but as power is calculated in a very small instant, so f is constant over here. So what we are getting, that is f dot dr dt, and we know that dr dt or dx dt or ds dt is equals to v, which will be equals to f dot v. This is the fundamental formula of power, that is power is equals to force into velocity, where v is equals to velocity. So by this we get some common units of power, that is our normal electrical unit, that is 1 kilowatt hour, which is equals to 3.6 into 10 to the power 6 joule. Some numericals also come from this by our simple practical environmental studies, that if suppose 20 units of current is consumed, then what is the bill? If the unit is 8 rupees 8 per unit, then what is the bill? This type of questions come. There is a very simple questions, and we know that this 1 kilowatt hour is equal to 3.6 to the power 6 joule is equals to 1 unit, 1 electrical unit. And there is also one important thing, that is horsepower. 1 horsepower is equals to 746 watt, and the unit of power is watt. As because we know that energy is equals to joule and power is equals to energy per unit time, so joule per second is also known as watt. So this is all about this entire chapter. In the next lecture we'll be dealing with some numericals on this entire topic. So thanks for watching.